Hey everyone, my name is Venerin, and in today's video we're going to build our first model using PyTorch. For that purpose, I've chosen this dataset called Palmer Penguins, and it's pretty amazing one. It is basically a dataset that tries to allow you to classify 3 different types of penguins or species of penguins, and the guys that provide this are essentially working on this dataset are called Dr. Kristen Gorman and the Palmer Station at Antarctica. So thank you guys for this dataset. The first thing that those guys are bringing us is the type or the species of the penguin. Then we have the island on which it was recorded, I guess. Then they're talking about the bill length and depth, also the flipper length and body mass in grams, and then the sex of the penguin. And they have a very nice illustration over here of the bill length. And essentially the flippers are the wings, if you will, of those penguins. So yeah, pretty much amazing data set. And right here I have a notebook which I'm going to share with you that is running on Google Co-op. And this is pretty much a freely available platform for you to try out and work on deep learning or Python projects, machine learning also, of course. So here thus far I have some libraries gdown because I'm going to download the CSV file that is provided by us. And then I have a couple of imports, Torch, Pandas, Matplotlib. We're going to use this in order to plot some data. Then I have TQDM. I'm going to show you what we are going to use this for. And then I have an inline of Matplotlib, so we can basically show the plots right here. So the first thing that I'm going to show you is how we can use Pandas to read the CSV file. We're going to use the read CSV method. And then I'm going to drop any row that has missing values. So this should give us 333 number of rows in this dataset. And then I have displayed this some of the data that we have here. As I've already told you, we have the species, the island, the bill dimensions, length and depth, the flipper length, and body mass in grams, sex, and the year in which the record was made. So this looks good. For the purpose of this video, we are going to use the flipper length in order to try to predict what is the body mass of the penguin. So here I'm going to use Pandas to plot this relationship. Flipper length in millimeters. And the body mass. And I'm going to specify the figure size. I want to be a bit bigger. And I want the size of the dots to be a lot larger as well. So here we have the relationship between the two, the body mass on the Y. As you can see, we have a wide array of weight for each penguins. Most of them are, like, I would say within 4 to 5.5 kilos. And then we have a good relationship between the weight of the penguins and then their flipper length. So you would imagine that when a penguin is heavier, since he or she is bigger, they are supposed to have bigger wings, if you will. We have very good separation of two, I would say, clusters here, but I'm not sure why this is the case. Maybe in later videos we are going to explore this in a bit more depth. So, as I've already told you, we are going to use the flipper length in order to predict the body mass of the penguins. And for this purpose, I'm going to use a very simple model called Simple Linear Regression. And this model works like this. we have some weights, which are parameters of the model. Then we multiply that by some data. In our case, the data is going to be the flipper length. And then we have some parameter called bias. So essentially what we are going to do in this model, or with this model, is going to be to create a straight line that tries to predict as much as best as possible what are the body mass compared to the flipper length. So we are going to construct a line, but we are going to do that using a model. So to create a model in PyTorch, there are some other ways as well, but I'm going to show probably the simplest one, and probably the more easy to understand. It is going to be extension or extending from the NN module, which is a PyTorch module. And I'm going to create a class. And I'm going to extend from this module. So here we are required to create a method called forward. And this method is going to take some data. And this is going to be of type torch tensor. And it's going to return torch tensor. So here I'm going to pass for now, since I need to create a constructor as well. And the first thing is that I'm going to call the super init. So the parent got initialized, and then I'm going to create the weights and the bias from here. So I'm going to initialize those using, again, PyTorch parameter. And I'll explain what this is in a second. But the documentation is already telling you that we should give it some data, and then whether or not it requires gradient descent, that is. And in our example, I'm going to pass in a tensor of 1 as a floating point, and I would like this to require gradient descent. All right, so we have the weights, and for the bias, I'm going to essentially do the same thing. Yeah. So the parameter is going to be, the weights parameter is going to be this weights, and the initial value is going to be 1.0, with the same thing for the bias. And those are parameters of our model, since we want to get the best possible values for those, or find the best possible values for those, in such a way that the line that we are going to build right here is going to be the best fit. That is the line that best describes this relationship between the flipper length and the body mass. So how we are going to find this line? We are going to use an algorithm called, or a combination of algorithms called gradient descent, and then we're going to use backward propagation. But I'm going to talk a bit more about those in a second. So let's finish this model. So instead of the pass here, I'm going to simply refer to the formula that we have right here. And I'm going to return the weights times the data plus the bias. All right, so this is the simple linear regression model, and it is simple because it has only a single weight as a parameter, and it's accept a single feature. In our case, this feature is going to be the flipper length, and we have only a single parameter for the bias as well. So it's really one of the simplest possible models that you can create. So to create an instance of this model, this is pretty similar to basic Python. I'm going to just initialize it. And if I print it, it's going to say just simple linear regression. But since we are extending for the NN module, we can actually take a look at the parameters within this model of ours. And I'm going to do that using the named parameters. And I'm going to iterate over those. So I'm going to print the name and then the data from the parameter. So as you can see, we have the weights, which is a tensor of 1, and then we have the bias with a tensor of 1. I'm going to open a note here about these ones, because most of the time when you're building some models, those values right here are going to be initialized for you. In this case, we just used a constant of 1, but that's not a very good practice. I mean, there are other ways to initialize those values, and usually those values are small, they're close to 0, and provide some randomness as well. I'm going to talk about initializing in later videos, but for now, we'll just have a look at what is the simplest possible initialization of those values, of those parameters. And in that case, I've chosen a constant of 1, but this have some inherent flaws. Just be aware of this for now. All right, so now that we have the model, we have the data right here. I'm going to need to get the data into a tensor format, and we've already seen how we can do that, but I'm going to show you how we are going to do this using the data frame that we have. I'm going to start with the flipper length. I remember those are the wings of the penguins, and I'm going to convert those to tensor. I'm going to do the same thing for the body mass. And I'm going to show you the shape of both tensors. Just to make sure that everything is correct, we have the same size. So the features which are going to be the flipper length, and the features are pretty much the data that we are going to use to train the model. And then the labels or the predictions that we're going to need to do are the body mass right here. So both of those should have the same length. And in this case, that is the case. All right, so now I'm going to pass the flipper length through our model in order to make sure that everything is working. And I'm going to take the predicted mass by passing in the flipper length. And this will be the predictions of our untrained model. And I'm going to show you why this is still untrained model. It doesn't have any magic behind it. I'm going to start by plotting a figure in order to get the results of the model. And this should give us a representation again of the dots from the data. And now I'm going to plot the predictions. From our untrained model. And as you can see, we have a straight line that is very, very far from the predictions that need to happen in order to have a good model that predicts the body mass from the flipper length. So let's see if when we train our model, our results are better. In order to train the model, I'm going to first make a section here. And in this section, I'm going to create two things. First, I'm going to create a loss function. and this is going to be mean squared error was and an optimizer. And this optimizer is going to take the parameters of our model and a warning rate. So what are those things and why do we need them? For the was function, essentially what we are going to do is when we are drawing this line, you can imagine that, how far each and every point in our data, how far away it is from the line that we drawn. The further away this line is from the dot that we are currently looking at, the more the error of our model is. So we would like to minimize that error in order to have a better one that better fits or describes the data. So you can imagine that right now the error is pretty huge, since pretty much every point from our data set is far away from this line. But even though that every line is far away, you can imagine that, for example, this dot right here has a much larger error compared to this one. Just because this is far, far away, probably probably like 2 times further compared to this one. So the error for this point is going to be larger. And essentially, this is what mean squared error was is doing, but it is working on a square, and it is giving us the mean of all points that we have. The formula itself, it's not that important. It's not that hard either, but this is the intuition behind this was function. So we're going to have to measure this error, and we have a way to do that using this MSE was, or mean squared error. And the next thing is the optimizer. So once we have this line and once we have this error, you would imagine that we would need a way to essentially change the parameters of our model so that this line is getting closer and closer to the points that we have in our dataset. So to do that, we're going to use this optimizer, and its job is going to be to find the parameters of our model that are much better so we can fit this line even better to our dataset. All right, so I'm going to go into much further details in later videos on both of those topics, but this is pretty much the components that we need to train our model. And the training, what I mean by that, I mean that we are going to find much better values for those parameters, the weights and the bias. We are starting with these constants, and then using some sort of search, if you will, which is the training itself. We are going to arrive at much better values that better describe the dataset that we have. So I'm going to start the training, and I'm going to record the losses during the training. And for the training, I'm going to iterate or train the model 100,000 times. Pretty simple thus far. And each time I'm going to take the predicted mass from the model by passing in the data. And then I'm going to calculate the loss using the loss function from the predicted mass to the actual body mass. And if I'm at 10,000 runs module, I'm going to record the loss. So next I'm going to do the training that PyTorch is requiring us to do. So first I'm going to do this zero grade or zero gradient. So if you're familiar with calculus, this will essentially zero out the gradients that the PyTorch accumulates during the training. I'm not going to enter into more details right now. Then I'm going to essentially tell was backward, which will execute this backpropagation algorithm for us. And then I'm going to call the optimizer.step. So if you think about it, the backward method right here is doing the following. Once we calculate the errors right here between the line and the dots, then our model needs to learn from this error. And the backward propagation algorithm is doing just that. Given the errors that we have, we are going to essentially teach the parameters about the errors that they're doing, and the optimizer is going to adjust those weights using the loss that we just calculated. So let me run this. And don't be afraid to not understand everything until this point, because this is very complex. And at this point, it might be a bit hard to understand what is happening right here. Of course, a much deeper dive might help you here. But at this point, we are going to treat this as a black box, as a way of train those models without necessarily understanding what exactly is happening under the hood. And then in later videos, we're going to go a bit more advanced and understand what and how things are happening behind the curtains, if you will. So the training is complete. This took us only 40 seconds. And then I'm going to plot the losses. This is why we recorded them. And yeah, as you can see, we have some decrease of the losses. And at some point, this pretty much flattens out. Of course, this is a good thing because we want the loss or the error that we have to decrease as the time of training continues. So this looks pretty good. Now I'm going to explore whether or not our model is better compared to before. And the first thing that I'm going to do is to get the parameter names again and the data. And since, if you recall, we have ones for the weights and the bias, now that the model is trained, these are the values that our training algorithm have found. So as you can see, we have a weight of 25 and a bias of minus 886. So these are very different compared to the previous values. And next, I'm going to take this chart right here, which compares the predicted and the real values. And I'm going to take the prediction of the model and paste it in here as well. So we're taking the predicted mass and running through the same plot. And yeah, if you recall, this is the initial line of the model with the initial values, and this is the line that is given by our model. So as you can see, this is much better compared to the previous results, and it looks like that the model has learned something, which is quite good. Alright, so in the next video we're going to continue with a bit deeper approach. We are going to have a look at why and how the optimizers are working, and we are going to have a look at the gradient descent algorithm, at least in some way or shape and form, how PyTorch is implementing all of this magic behind the curtains, if you will. So I'm going to also show you how you can build your first neural network using PyTorch and how we can probably increase the accuracy of our model and what we are going to do in order to do some classification as well. Thanks for watching, guys. Please like, share, and subscribe.